In the last part or last video, we looked at the derivatives of e to the x and the natural log of x. And those were very interesting derivatives, but now we want to actually move to more arbitrary cases of a to the x, where a is just any number you want, and the natural log base, or not the natural log, the log base a of x, right? And if we plug in e equals a, then we get the derivatives of e to the x and the natural log of x. But now we want to actually step away from just an easy case and move towards a more arbitrary or abstract case of any a we want. So here we go. I'm going to prove both of these differentiation formulas, and then we're going to do some examples. So derivative with respect to x of a to the x. And we cannot just use the power rule, right? We cannot, because x is changing. It's not a number. It's not like 2. If it was, then it would be, if it was x squared, then we can use the power rule, but it's a to the x squared. Now the x is on the, I guess the power is the power, so we cannot use it's not as easy as the power rule. How do we go about this? We don't even know the differentiation formula of a to the x, but we do know the differentiation formula of e to the x. Can we use that to our advantage? Let's see. Well, one fact I know about e to the x, if I took e to the natural log of any function, the natural log and the e cancel out, and I'm left with the function. This is the, I guess, the property of an inverse function. Can I use that to my advantage? Let's see. Well, can I just make the function equal to a to the x? Maybe. I actually can. So the derivative with respect to x of e to the natural log of the function e to the x. And now I actually can use a property of logs where the power can just hop down in front. So it's in reality equal to the derivative of e to the x times natural log of a. And see how we just got from not even knowing what the derivative formula is to something that's more manageable, because we do know the derivative of e to a function. I'm going to erase this so I can write below this. Another note I want to make is, remember e to the function, we want to find its derivative. So what's the derivative with respect to x? This is some side thing. E to the function. In the last video we actually found it to be, the function or the power is the inner function. So we want to keep that the same, and then multiplied by the derivative of the inside, which is the power. So we're going to use that. We're going to use the chain rule to this right here. We're going to use the chain rule. So I'm going to erase this now, so I can have space here. The derivative with respect to x of this, e to the x natural log of a. Now I want the derivative of the inside. And notice that we can actually find this, because natural log of a is a constant in this case. So I can take that out, and I'm just finding the derivative with respect to x. In other words, e to the x natural log of a times 1 natural log of a. And can I simplify this any further? In fact, I can. I notice that the e and the, I guess, the natural log cancel, but the x still stays there, but the inside here actually becomes a real function. In other words, it's equal to a to whatever's left over, which was x, times the natural log of a, and that's the result. In all, we get the derivative with respect to x of a to the x is equal to itself times the natural log of a. So it kind of ties in with this idea of the derivative of e to the x, but we actually just multiply by the natural log of whatever it is. And we can actually check, we can verify. Let a equal e. So we get e to the x times natural log of e. Natural log of e is 1, so we're left with e to the x. So this is a true statement. So it actually kind of double checks us, because we do know the derivative of e to the x being itself. So the derivative of a to the x is just itself times natural log of whatever that base is. And now I want to prove the other one. dx of the log base a of x. So let's begin. We are going to take advantage of something called change of base. change of base, log, so this is some side. Remember, we can change it to anything we want. I'm going to make base e or just natural log. This is what I'm going to take advantage of. So we're going to rewrite this as a derivative with respect to x of the natural log of x divided by natural log of a. In other words, the natural log of a is the constant, so we can take that out. Natural log of a dx of the natural log, and we know this. This is actually really easy. I'm going to erase this now. It's equal to 1 over natural log of a. The derivative of natural log of x is 1 over x. In other words, it's 1 over, I'm going to move the x to the front, natural log of a. And there we have it. The derivative with respect to x of log base a of x is equal to 1 over x, so we kind of retain that natural log derivative. But then we just, same thing like the exponential, we just introduce this term, natural log of whatever that base is. And then again we can verify, if I plug in e here, this becomes e and this goes away. So it's a double checker. So there we have it. The derivative I have right here, this is the important one, right here and right here. So we're going to do a couple examples using these. So let's begin. Okay, so we're starting off with a very tricky one, meaning that it's not just finding the derivative, it's actually finding the slope of 21 at what point. So at what t value does that happen is what we're basically trying to find out. And remember, slope is tied to the derivative, so we actually want to take the derivative. So y prime is equal to, what's the derivative of 2t? Well, from my formula, the derivative with respect to x of a to the t is equal to, or a to the x, is equal to a to the x times the natural log of a. So it's, in this case, it's the same thing times the natural log of the base, 2. And then the derivative of -3 is just 0, so we're left with this. When does this, which is the slope formula, have the slope of 21? In other words, when is it equal to 21? We want to just basically solve for t. So this is just a good review of solving equations that deal with exponentials and logs, but there's no logs in this case, it's just exponentials. So let's isolate the thing that has t with it. And then how do we get rid of the 2 or the 2t? Well, we take the natural log of both sides. Natural log, natural log. So when I take the natural log, the t actually just hops down, right? Using the property, t natural log of 2 is equal to the natural log of 21 divided by the natural log of 2. So we have a natural log inside of a natural log, kind of weird, but it's fine. T is equal to natural log of 21 divided by natural log of 2, all divided by natural log of 2. And I guess if you really wanted to, you can plug this into a calculator. I have the answer here. It's about 4.921. So at t equals 4.921, the slope of this function is 21. I guess I can plug it in also to y to get the point. So y equals to 4.921 minus 3, which is equal to 27.297. So at this point, 4.921 comma 27.297, the function has a slope of 21. And there we have it. It's kind of weird to see decimals, and some of the problems can actually get pretty nasty looking with the algebra or with the expression here, right? We have a natural log instead of a natural log, but as long as we're applying algebra correctly, we should be fine. And that's it for this problem. Let's do one more. There is a trick with this problem, and if you know the trick, I highly encourage you just to use the trick. But I'm going to show you the regular way, and then I'm going to show you the trick that maybe you should have known, but a lot of people end up missing it. So we're going to take what's called a long way, and then I'm going to show you the short way. So find dy dx if y equals this, log base a of a, sine of x to the sine of x. Here we go. The derivative with respect to x of this function, log base a sine of x, is equal to, if you recall, the derivative with respect to x of log base a of x is equal to 1 divided by x natural log of a, or whatever the base is. So we're going to apply this. So it's equal to, so x in this case is this whole thing, right? It's the input to the function. So it's 1 divided by a to the sine of x times natural log of a, and then multiply by that chain. We cannot forget that. So the chain is a to the sine of x. So we want to find the derivative with respect to x of a to the sine of x, right? We're getting a hairy problem in our case. The derivative of a to the sine of x, so I'm going to write it here again. The derivative with respect to x of a to the x is equal to a to the x times natural log of a. So let's continue. The derivative here, so I'm going to just bring this down, is a to the sine of x times natural log of a, and then we have to multiply by the chain since the power is a function. So this derivative of this is cosine of x. So now this is the side work. That's a weird asterisk, but whatever. So let's drop this down. Oops, there we go. Let's drop this down. So I'm gonna, I guess, continue the equal sign right here. Is equal to 1 divided by a sine of x natural log of a multiplied by the chain, which is found to be a to the sine of x natural log of a cosine x. And then we see a lot of stuff cancels out, so I'm going to scroll down. This cancels out with this, and this cancels out with this. We're left with cosine. And that's kind of a weird occurrence, because we just did a lot of work and just ended up with cosine. And that's where the trick actually comes in. If you didn't notice, I'll actually tell you. So here we have it. It's not the natural log. It's the log base a of a to the sine of x. The trick here is to first use the, I guess, the log property that the power, right? We can bring the power out. So sine of x log base a, and maybe you see it here now because it's not as complicated. Notice that we have the same base in the same entry, a, and that's the actual idea of log. There's a property that says if you have the same base as this, it goes to 1, because we can even verify itself. If we change the exponential form, x to the first power is equal to x, that makes sense. So that's the trick. This goes to 1, and we're actually just finding the derivative of sine. So I went through the long way just to show you how to find a derivative of a log function, but I also wanted to show you that not all functions don't need to be as complex as they should be, right? You don't want to do all this work, but I just did it here. I would rather just notice that I can use a property here, and boom, I'm just finding the derivative of sine. Easy. But it's good that I did this, because it's good practice just to find the derivative of log functions. And now, since we actually finished this video, we actually, I covered all the differentiation formulas: power rule, quotient rule, chain rule, and product rule, but I also found the derivatives of trigonometric functions, derivatives of polynomials, derivatives of inverse trigonometric functions, exponential and logarithmic. We also talked about implicit and inverse functions, and that's all the derivatives you'll actually encounter in a calculus course, or an introduction, our first semester calculus course, calculus AB. That's all the derivatives you actually run into. It's just that they're going to be put into many different combinations that you have to apply specific rules to. So this is actually the end of derivatives for differentiation formulas and techniques. So maybe in the next time I'm going to go through a bunch of review, just going through random derivative problems just to see how to approach problems and just go through a bunch of them. So this is actually the end of differentiation formulas, which covers a lot of differentiation formulas, but that's it. So next time we're going to do a bunch of problems just with derivatives, any type of derivatives. That's it for this video.